So, Paul, we've learned that the universe started in something like a Big Bang and that the universe is expanding. But what we haven't learned is how that expansion changes over time.
Well, we can think of this in terms of a scale factor. So here's a scale factor of the universe. Remember, we multiply all coordinates by the scale factor, and so as the scale factor gets bigger, everything gets further apart from everything else. This is one way of seeing the expansion of space. And what we know is that right now, at time today, the scale factor is getting larger with time. The universe is getting bigger as time goes forward. But what's it do earlier and later? Well, the simplest possible assumption would just be this, that A of t is proportional to time, so a linear relationship, a straight line relationship. This actually isn't possible. This would only be the case if the universe didn't have any forces inside it. But let's look at the consequences of this for a moment. If this is the case, then we could look at the current expansion rate of the universe and extrapolate back to find out when the universe was formed. That would be a pretty neat thing to know, the origin of the universe. That's something that philosophers have been debating for centuries.
Yeah, and this is the way I like to think of it. Imagine you have a galaxy right now that's some distance at some time. Time is right now. And we remember that when we go through and we look at galaxies, Hubble saw that they were more or less moving away from us. Now, we know that that motion is really light being stretched because the scale factor is changing, but we can also think of it as a velocity. And so you expect the velocity to be changing in time using the same relationships we'd use for a projectile here on Earth. And therefore, we can run the universe in reverse. We can back it back in time. And when we calculate when this galaxy is at the same place Earth is, then we know we are at the time of the Big Bang. Now, this distance, if you think about it, is the same as scale factor because the galaxy is getting closer because the scale factor is getting closer. And so let's go through and do what I did during my PhD thesis here with my supervisor, Bob Kirshner at Harvard. I went out and I measured the scale factor, or the Hubble constant as we like to call it, back in time. We measured how old the universe was.
So let's try to measure the age of the universe from the distance to this galaxy. Now we know that the distance over a function of time is where you start plus your velocity times time. The time of the Big Bang, well, we know that the distance from us to that galaxy, we want that to be equal to 0. So that allows us to solve this equation in the form of t, such that t is equal to minus d divided by velocity. The minus sign means we're looking back in time, so let's not worry too much about that minus sign. Another thing to keep track of is we define something in a cosmology known as the Hubble constant. The Hubble constant is how fast the universe is expanding right now, and we normally write it down as being the redshift in terms of kilometers per second, so that is c, the speed of light, times the redshift, divided by the distance, so cz divided by d. And you will note that that cz is velocity, or v, divided by d if you equate the redshift with velocity. So given what the Hubble constant is, you can see that t is also equal to 1 over the Hubble constant. Now, let's use my galaxy now to measure the age of the universe. So the distance to the galaxy is 115 megaparsecs. And the v, or cz, is equal to 7,800 kilometers per second. So if we do a little calculation, we get that t is equal to d, 115 megaparsecs, divided by v, 7,800 kilometers per second. That's not a very useful set of units, megaparsecs per kilometers per second. So let's multiply by the fact that there is 3.09 times 10 to the 22 meters per megaparsec, and change kilometers per second also to reflect the fact that there's times 10 to the 3 meters per kilometer. Now, if we multiply that all out, we get 4.6 times 10 to the 17 seconds. There are, of course, or maybe you don't know this, 1 year is 3.16 times 10 to the 7 seconds. And so this equates to 14.4 billion years. So in other words, if a galaxy is moving away from us at 115 megaparsecs and is traveling at 7,800 kilometers per second, that galaxy would have been where we were 14.4 billion years in the past. Here's another way to think about how old the universe is. 115 megaparsecs, if I want to convert that to light years, I need to multiply by the fact there's 3.26 times 10 to the 6 light years per megaparsec. And I find that we are at 115 megaparsecs, 3.75 times 10 to the 8th light years in distance. In other words, light has been traveling for 3.8 times 10 to the 8th million, 3.8 times 10 to the 8th years between us and that galaxy. The other thing to keep in mind is that 7,800 kilometers per second is equal to the redshift, CZ, or in dimensionless units, that corresponds to 0.026. So, remembering that the scale factor is equal to 1 over 1 plus z, and that can be approximated by 1 minus z, that is 1 over 1 plus z if z is nearly 0 is equal to 1 minus z, then we see that the scale factor was 2.6% smaller at the time the light was emitted from this galaxy. So 1 over 0.026 is 38.5. In other words, we have to go 38.5 times further back in time to when A is equal to 0, the time of the Big Bang. So if I take the time of the Big Bang to be equal to 38.5 times 3.75 times 10 to the 8th years, I get, voila, 14.4 billion years. Same answer we got before, a slightly different way to think about it.